we will like to find the geometric meaning of a differential equation. So we first consider the differential equation dy by dt is equal to minus 2 times y. So in this differential equation, when you take a particular value of y, then from the right hand side of the differential equation, we obtain the value of dy by dt. For example, if I take y to be equal to 1.5, then the right hand side of the differential equation is minus 3. So that means that dy by dt is minus 3, which means the slope of y is minus 3 at the point where y is equal to 1.5. So we can plot this. So let us look at this diagram, which is the diagram representing the differential equation dy by dt is equal to minus 2y. So we plot the t on the horizontal axis and y on the vertical axis. So when y is equal to 1.5, here the slope is minus 3. So at all this point along this horizontal line, the slope is minus 3. So we put short lines, short arrows all along this wherever y is equal to 1.5. So displaying this information graphically in the ty plane by drawing short lines, segments or arrows at several points on y is equal to 1.5. Similarly, we proceed for other values of y. So you see this diagram. Now suppose you take the value of y to be 1. So all along the points where the value of y is 1, we get dy by dt to be equal to minus 2 times 1, that is minus 2. So we draw short arrows whose slope is minus 2 all along this. Again, now you can choose another value of y, let's say 0.5. Then dy by dt comes to be minus 1. And so we draw arrows all along this points where y is equal to 0.5 and the slope of those arrows are taken to be minus 1. So in this way you can draw several arrows, short arrows, which gives the slope according to the differential equation. So this figure given in the next slide which I showed to you, and there is another slide where I'll show, this is called direction field or slope field. The short arrows throughout the picture, that are called direction field or slope field, the entire picture. So that describes the differential equation. Now many times along with those short arrows, we also draw series of lines along which the arrows have same slopes. So these are called isoclines. So isoclines is a series of lines with the same slope is often used to supplement the slope field or direction field. So in the equation of the form dy by dt is equal to f of t comma y, the isocline is a line in the ty plane obtained by setting f of t comma y equal to a constant value. Like last time we were choosing the constant to be particular value and that was becoming the slope. So in this diagram we saw that the isoclines, this colored straight lines, they are the isoclines. In this figure we saw those isoclines are parallel to the t-axis, but it may not be the case for all differential equations. Now here the differential equation dy by dt is equal to minus 2y is an easy equation to solve, easy differential equation to solve. But many a times the differential equations have complicated solution formulas, or sometimes they don't have explicit solution at all. By explicit solution, I mean the solution can be written in the nines form. Such solution don't exist. Then, with the help of computer, we plot the direction field and the isoclines, and from that we can interpret what the solution is. For example, if we join these arrows so that in a smooth way, if we can join, each of them give a solution of the differential equation. For various initial conditions, we get various solutions through it. So if we join like this will give you one solution. You know what is the solution of this differential equation? Dy by dt is equal to minus 2y. This is the same kind of equation which we used for radioactive decay, where the decay constant is minus 2. You know, it's a solution is of the type y is equal to c times e raised to minus 2t. So these curves are actually the curve of e raised to minus 2t. We see the next differential equation. So the question is, find the curve through the point 1, 1 in the xy plane, having at each of its point the slope minus y by x. The curve should pass through 1, 1. So it's giving an initial condition, and it is telling us that its slope is minus y by x. So this gives us a differential equation. So y dash is equal to minus y by x. The slope is equal to minus y by x. This is the differential equation. And the initial condition is what? Initial condition is y of 1 is 1. Now by inspection, this equation has a solution y is equal to c by x. With some effort, by inspection, you can find that this actually is the solution. You can differentiate this particular expression and see this actually satisfies this differential equation. Later we'll see how to solve this kind of differential equation in a general way. There is something called solution by separation of variables that we'll do. Anyway, by inspection, we get this solution here, y is equal to c by x. And this is a general solution of this given differential equation with arbitrary constant c. So y is equal to c by x describes a family of hyperbolas depending on the constant c. Now when you apply the initial condition to it, namely y of 1 is equal to 1, what do you get? If y is equal to 1 and x is equal to 1, that means the c is equal to 1. Right? So we substitute c is equal to 1 in the given general solution, we get y is equal to 1 by x. So y is equal to 1 by x is the solution of the differential equation which satisfies the initial condition that it passes through the point 1, 1. Now for this differential equation also, we would like to plot the direction field and get the isoclines also. So what is shown in this picture are the is the direction field of the given differential equation. Dy by dx is equal to minus y by x. The x is plotted along the horizontal axis and y is plotted along the vertical axis. Here you can see for this differential equation, when value of x is equal to y, this will have slope minus 1. When y is 2 times x, this will have slope minus 2. When y is 3 times x, this will have slope minus 3, and so on. So the isoclines are straight lines passing through the origin and having some slope. The straight line passing through the origin. You can see along these isoclines, the arrows are having same slope. So looking at the isoclines and looking at the slope, we can plot the slope field. Since you have seen two slope field or direction field, the concept must have been clear now. Now, initial value problem, we saw that many times we are able to determine the arbitrary constant that is coming in the general solution. But it is not always the case. An initial value problem sometimes may have no solution, as you see here, and sometimes it can have unique solution where you can determine the constant, and sometimes it can have infinitely many solutions. So the first example where it has no solution is differential equation is absolute value of y dash plus absolute value of y is equal to 0, and the initial condition is y0 is equal to 3. So this differential equation that is given here will not satisfy this initial condition. No solution will satisfy this differential equation, because if the value is 3 at a point, its absolute value plus absolute value of its derivative, which is a positive quantity, 0 or a positive quantity, cannot be, the sum cannot be equal to 0. So this initial value problem does not have a solution. Now here is an example of an initial value problem which has a unique solution. So differential equation is very simple. Y dash is equal to x, and the initial condition is y0 is equal to 1. This has a unique solution. You can find out what the solution of this differential equation is. That solution of the differential equation will be y is equal to x square by 2 plus c, and when you substitute y0 is equal to 1 in this differential equation, we get, since the equation is y is equal to x square by 2 plus c, when x is equal to 0 and y is equal to 1, we get c to be equal to 1. So the solution of this differential equation is y is equal to x square by 2 plus 1. It's the unique solution. Now, sometimes the initial value problem may have infinitely many solutions. Look at this example. X times first derivative of y is equal to y minus 1. And the initial condition is y0 is equal to 1. The solutions of this differential equation turns out to be y is equal to 1 plus cx. You can check that this satisfies this differential equation. What you do, you have to take the derivative of y and then do manipulation so that you remove the constant c, and then you will get this solutions, this differential equation. So this particular expression is the solution of this differential equation. Now in this solution, this general solution, if you substitute y0 is equal to 1, what happens? So when x is equal to 0 here and y is equal to 1 here, we don't get any value of c, because c times 0 is 0, so we get y is equal to 1, so 1 is equal to 1. So initial value satisfies this equation, but then it does not give us any value of c, means all value of c will satisfy this initial condition. Suppose you take c to be equal to 4, then y is equal to 1 plus 4x satisfies this initial condition, because 0 times 4 is 0, plus 1 is 1, and y is equal to 1. So it satisfies the initial condition. So for any value of c, this is a solution. So it has infinitely many solutions depending on its choice of c. So initial value problem can have no solution, precisely one solution, or infinitely many solutions. So this motivates us to find out the conditions under which the solutions will first of all exist, and then if it exists, what are the conditions under which the solution is going to be unique of an initial value problem. So our approach here will be that we'll first look at some methods of finding solutions of first order ordinary differential equations, discuss the general geometrical meaning of the solutions, and then we proceed on to study the existence uniqueness result of the initial value problems. Consider an ordinary differential equation of the form mx plus ny times first derivative y is equal to 0. This particular kind of ordinary differential equation is called a separable ordinary differential equation. This kind of ordinary differential equation has a very easy method to solve them. So m is a function of x, n is a function of y is the dependent variable in terms of x, and it's the first derivative of y with respect to x, y dash. So we assume that mx and ny are nice functions. Let us say they are continuous functions. So let h1x and h2x be functions such that its derivative is mx and derivative of h2y is ny. This m and n are nice functions. There are functions h1 and h2 whose derivatives are m and n respectively. So these are the assumptions that we make on this ordinary differential equation. Then it is quite easy to solve this differential equation. We substitute mx is equal to h1 dash x in the given differential equation, and we substitute ny is equal to h2 dash y in the given differential equation. So the differential equation looks like h1 dash x plus h2 dash y times y dash is equal to 0. Now here we can apply chain rule to the second term here, and by chain rule we get the derivative, the dh2y by dx is equal to derivative of h2 with respect to y times derivative of y with respect to x. That is the chain rule. So what is appearing on the right of this yellow box is the term that is there in this differential equation. So we substitute this particular expression from the yellow box into this above equation. What we get is d by dx of h1x plus h2y is equal to 0. So derivative of some quantity is equal to 0. Here this is a function of x and h2 is a function of y, and y is again a function of x because y is a dependent variable. So derivative of certain quantity with respect to x is 0 means that quantity must be constant. So h1x plus h2y is equal to c, where c is arbitrary constant. So this h1x plus h2x equal to c is the solution of the given differential equation. So we have described one method of solving certain differential equation. So these methods many a times gives us implicit solution and not necessarily an explicit one. For example, the expression h1x plus h2y is equal to c is an implicit solution. It doesn't express y explicitly in terms of function of x. We'll see examples. The first example is y dash is equal to minus 2xy. If we want to write it as mx plus ny y dash equal to 0, so this is what you get. We just divide y dash by y, and then this y dash we replace it by dy, and dx we take it on the right hand side. So here you see on the left hand side we have a function of y only, and on the right hand side we have a function of x only. That is what we wanted in the previous method. Mx is a function of x only and ny is a function of y only. Then we can solve it. So we arrived at that expression like the previous slide. So this is a separable ODE, and the function 1 by y and minus 2x, they are very nice functions. So we just integrate it to find out the h1x and h2y respectively. So we don't have to involve those h1x and h2x. We can just directly integrate the given differential equation, and we get the left hand side of this dy by dx. When you integrate, you know that it is log of mod y, and right hand side is minus x square. So it is minus 2 times x square by 2, 2 cancels, so we get minus x square plus a arbitrary constant c1. Now here, since this is in terms of logarithm, if we want to remove the logarithm, we have to write y mod y is equal to e raised to whatever is there on the right hand side, e raised to minus x square plus you can multiply that with another constant c. So here we don't need the modulus because e raised to minus x square is always a positive term. So y is equal to c times e raised to minus x square is a general solution of the given differential equation. Now we are interested in how does it look, a geometric interpretation for this solution. So this was a differential equation, it has arbitrary constant. Now we would like to put some initial conditions on this differential equation. Let us say the differential equation at a point x0 takes the value y0. So y of x0 is equal to y0 is the initial condition that we are giving to this ordinary differential equation. So that means what? In this given solution, we get y0 is equal to c times e raised to minus x0 square. So if we take the e raised to minus x0 square on the other side, we get c is equal to y0 times e raised to x square. So we have determined the value of c in terms of the given initial condition y0 and x0. So we substitute this value of c back in the given solution here. So this will be y is equal to y0 e raised to x0 square times e raised to minus x square. So in total the solution will be y is equal to y0 e raised to x0 square minus x square. In particular, if we take the initial condition in the following way, namely y0 is exactly equal to e raised to minus x0 square, then what will happen? Y0 is replaced by e raised to minus x0 square. So this two product will give you 1. So c will be equal to 1. So the solution is, if c is 1, the solution is y is equal to e raised to minus x square. So we want to plot y is equal to e raised to minus x square. It turns out that if you plot this function fx is equal to e raised to minus x square, then it looks like this clearly. So e raised to minus x square is always positive, and if you plot you will get this. And now how to find the area of this? You can take it as an exercise how to find the area under this curve. There is a very interesting way of doing it, something which involves polar coordinates to integrate. Integration of two variables, and then you can convert that into polar coordinates, and very easily you can find the area under this curve. So integration, you can integrate this and find out the area. I leave it as an exercise. We go to the next example. Find the solution of the initial value problem dy by dx is equal to y times cos x divided by 1 plus 2y square, and the initial condition is y of 0 is equal to 1. So we assume here that y is not equal to 0, because when we separate the variables here and apply the previous method, we have to divide it by y. So we don't want the denominator to be 0, so we assume y is not equal to 0. Please note that y is equal to 0 everywhere is a solution of this differential equation. The numerator is 0 and denominator will be 1, and the left hand side is can be taken to be 0 because y is constant 0. So y is equal to 0 everywhere is a solution of this differential equation. But that solution will not satisfy the initial condition y0 is equal to 1. Okay, we'll come to that later. We separate the variables, we transfer the denominator here to the left hand side, the y to the numerator to the left hand side, and arrange it, transfer the dx on the right hand side, you get this expression. Now we can easily integrate this expression. So integration of 1 by y will give you log y. Integration this 2y square by y is 2y. Its integration will give you y square. Integration of cos x will give you sin x, and there will be arbitrary constant c. So here this is the solution of the given differential equation, and then we put the initial value to this solution. So initial value is y0 is equal to 1. So put x is equal to 0. So sine 0 is 0. Y is equal to 1. So y square is 1. Log of 1 is 0. So you have 1 is equal to 0 plus c. So c is equal to 1. So when you substitute c is equal to 1 in this expression, we get log mod y plus y square is equal to sin x plus 1. So this is the solution of the initial value problem. And as I remarked in the beginning, y equal to 0 everywhere is the solution of this differential equation, but it does not satisfy the initial condition y0 is equal to 1, because if you take this y everywhere 0, then y at 0 also should be 0 and not 1. So this cannot be a solution.